Oh, there you go.
Oh, okay.
The life of an AV guy only stops working when you go to use it. And, well, there's another one here too. There you go. So.
Okay.
I will wait.
Yeah.
I'll just start it. Is that okay?
Yeah.
Oh, well, no, I won't because it flips. You're not giving a talk today. Did you know that? Right now, I don't know if you know this, but there's a gentleman coming up in this speaker view. Play that, or do you want full screen?
All right, welcome to day 3 of our workshop. You may remember me from before. I'm Will Fisher. I was the low mass implementation lead for Ulysses. And we have a bit of a thematically linked session of talks today, looking at the impact of UV on disks and planets. We will get started with the talk by Nicole Arulanantham from here at Space Telescope. And Nicole, go ahead when you're ready.
All right, thanks, Will. Can everybody hear me okay? Okay, awesome. So I wanted to start the talk, since we have a pretty broad range of science interests in this room, I wanted to start the talk with just a very broad overview about why we care about the UV radiation field in protoplanetary disks. I clearly missed the memo about everybody using the Hartman diagram. But I wanted to share this graphic. This is an excerpt of the recipe for planet formation graphic that was made with input from the Office of Public Outreach here at STSDI. And so we're looking at steps 2 through 3 here. So when your molecular cloud starts to collapse, you'll start to form a star at the center. And you won't be able to see the star for a while. It'll still be surrounded by an envelope of gas and dust. But eventually, this gas and dust will flatten out into a disk, and this is what we see here. So we'll have a star at the center surrounded by a disk that contains the materials that will eventually form planets. And so when we think about the low mass stars in the Ulysses sample, this is what we picture. And as we saw in the talks over the last couple of days, this distribution of dust and gas is not always going to be this nice and smooth, right? We're going to see cavities, gaps, rings, spirals, all kinds of structure. But this is the basic picture. So when we think about planets forming in these disks, one kind of guiding question that we have in mind is kind of what we would see if we were looking for a habitable planet. And we have one very nice example. I will say one big perk of working here in Baltimore is that Baltimore has a really thriving arts community. And so I wanted to share this beautiful photo of the northern lights that my friend Margaret Rorison took in Iceland this past January. And it's a nice reminder of the ingredients in our atmosphere that make our planet very friendly to us. So we know we have a lot of oxygen and nitrogen, and we also have a lot of water. And so we have a good sense of what ingredients we needed to make our world habitable. And when we look in the bigger picture, we have a few really big questions when we think about habitable worlds in other places. Now, one question that we ask in the DISC community is where these ingredients came from. And this is something that we're really starting to answer very nicely with observations from JWST. So this is an example of a water spectrum, so actually a water spectrum from 2 different protoplanetary disks. And this spectrum comes from MIRI observations that were acquired as part of the JWST Disk Infrared Spectral Chemistry Survey. So this is a collection of Cycle 1 and Cycle 2 GEO programs containing about 30 protoplanetary disks. And so we're really able to see some nice trends here. And what we see when we look at the spectrum of water vapor with JWST is this beautiful resolved spectrum. And the sensitivity and the resolution of this data is so high that now we can actually distinguish different thermal components in this population of water in the protoplanetary disk. And so we see this white spectrum here is consistent. Sorry, the pointer's going all over the place. This white spectrum here is consistent with a very warm population of water vapor. So this is about 800 or 900 Kelvin gas. And we can actually see excess emission that's consistent with cooler material that would be a little bit farther away. And so with JWST now, we're really getting a good handle on what these ingredients look like in protoplanetary disks, very close to the star where we would expect rocky planets to be forming. Now, another question we might ask is how these ingredients are distributed throughout the solar system. And this is another really awesome thing that the solar system community is making leaps and bounds in measuring with JWST. I love looking at this image. This is a JWST image of the moon Enceladus. And we see this gigantic plume of water vapor. So all of this kind of blue stuff on the image is water vapor that's just being blasted out of this moon. And you'll notice that it goes right down to the edge of the detector, right? Nobody realized that this plume was going to be so extended. And so we're really getting a nice constraint on where really vast amounts of water vapor are hiding elsewhere in the solar system. And when we think about exoplanets, we can also see signatures of water in their atmospheres too with JWST. So this is an example of a transmission spectrum from a giant planet. And when we look at the atmosphere as a function of wavelength, we see these peaks in the spectrum, and this corresponds to wavelengths where the measured radius of the planet is larger because molecules in the atmosphere have absorbed light from the star. And so we can see these really nice peaks from water, carbon monoxide, carbon dioxide, and what was really exciting about this planet was the detection of sulfur dioxide. So we're getting a good handle on where the water, the carbon, the oxygen, the sulfur, all of these nice ingredients are. So I've shown you a few things here, right? We can see water in protoplanetary disks to map out the initial conditions. We can see water across the solar system to try and understand how these ingredients are distributed throughout the planetary system. And we can see water in the exoplanets. But that leaves us in a bit of a sticky situation, right? Because we have water in all of these different environments, and it's still very, very difficult to understand how one thing got to another, right? We don't really know how the initial conditions in the disks translate to the atmospheres of the exoplanets that we're observing today. We don't really know whether our solar system is reflective of conditions everywhere in the universe, right? And while the Ulysses data won't help us answer everything, it can help us start to get a handle on what's happening in these disks, particularly in the regions very close to the star. And I think James Owen after me is going to talk a lot about how the UV radiation field impacts the evolution of planets. Now, the process of mapping chemical conditions in protoplanetary disks is wildly complicated. So if you feel overwhelmed by this plot, Don't feel bad. I also feel a little bit overwhelmed by this. This is a beautiful figure from Karin Oberg's recent review paper. But I'll focus on the pieces of disk chemistry that the Ulysses data can kind of help us start to get a handle on. And we saw a really nice overview by Nuria on Monday. We heard about disk wins from Uma Gorti on yesterday. And I'm going to focus today on how the heating and radiation from the central star impacts the gas in the protoplanetary disks. And later today, we'll also hear some talks in these same areas by these people up here. Okay, so we could spend a whole conference, of course, talking about observations of protoplanetary disks in the infrared. But in the Spitzer era, there were a few really interesting trends between the detection rates of different molecules in disks and the inferred UV radiation fields from the central stars. And these results can be summed up nicely in this set of models by Catherine Walsh from 2015. And so each of these panels here is showing a 2D cut of a protoplanetary disk. So we're looking at the height above the disk midplane on the y-axis and the distance from the central star on the x-axis. And on the left-hand side here, we're looking at a disk model with a radiation field from a typical M dwarf. In the middle, we're looking at a disk with a radiation field from a typical T Tauri star. And on the far side, we're looking at a disk surrounding a typical Herbig star. And you'll see that the red here is tracing where the abundances of, for example, HCN molecules are quite high. And so we can see a lot more emission from HCN in the M dwarf disk. This is suppressed in the T Tauri disk, and it's missing in the surface layers of the Herbig disk. And this model was used to explain the detection rates of these molecules around different types of stars. So in the disks around the M stars, there was a very rich carbon chemistry that was observed, so there were much higher detection rates of molecules like HCN and C2H2, and very little water. Whereas when we go to the T Tauri disks, we see a lot more water, but maybe fewer detections of these carbon-bearing species. And then in the Herbig disks, we see a pretty flat spectrum where there's really nothing there. But there were already kind of a few complications. So in this plot, we're looking on the y-axis at the luminosity of the HCN emission lines from Spitzer. And on the x-axis, we're looking at the observed FUV luminosity as measured from spectra from COS. And we can see, actually, that instead of a decline in HCN as we go to higher UV radiation fields, we actually see an increase. And one thing that was very challenging with Spitzer spectra was that the resolution was a bit too low to really carefully constrain the abundances or even the column densities of HCN and other molecules in the disks. And so it's quite possible that this is just a function of heating, that you have some reservoir of molecules in your disk, you make them hotter, and they produce more emission. But this is something that is a bit challenging to untangle at the resolution of Spitzer. So we go to JWST. And I wanted to show this beautiful spectrum of the disk around SZ114, which is actually a Ulysses target. And this is a disk around an M star. And we can see this really nice, beautiful, high-resolution band of C2H2. Then we can also see the HCN. And we're starting to resolve really nice structure in these bands that help us get a handle on the column densities and the temperatures of the emitting gas. We also see this really nice bright CO2 band. But if we look at the bottom panel, we see something that was pretty unexpected for the M dwarfs. We see a water emission line, and it turns out that this is actually a very water-rich disk around this M star. Okay, so that's a bit funny. And there are a few things that could play an important role here, right? One thing is the structure of the submillimeter disk. But the thing that's probably most relevant for us to think about here is actually the accretion rate. So this M star actually has an accretion rate that's more typical of a K star. And so we have this really nice warm radiation environment, and then we see this beautiful water spectrum. And so it's starting to become clear that we can't really look at the spectral type of a star and from that spectral type alone infer what the disk is doing, right? We really need to actually observe the UV radiation field to map out what we're going to see in the disk. Okay. Now, one thing that I think is particularly interesting is that in these models, Catherine Walsh did a really nice job of approximating the UV radiation field. So as we've seen in previous talks, chemistry in disks is a very complicated radiative transfer problem. And if you add in Lyman alpha, which is typically the brightest emission line in the spectrum, you end up with a much more complicated problem because Lyman alpha radiative transfer on its own is an entire field of science, right? But what this paper did for these models was assumed a black body component for the bulk of the UV continuum. And so we can see the fainter M dwarf, the T-Tauri disk in the middle, and the Herbig star on top. And then to approximate the Lyman alpha emission line in these models, a simple symmetric Gaussian profile, emission line profile was used. And the Gaussian emission line profile was scaled to have the flux that would make it comprise about 75% of the total UV radiation field. So if you added up the flux from each of these emission lines and compared it to the total spectrum from about 912 to 2000 angstroms, you would get about 75%. And so the assumption here is that the Lyman alpha line also scales with the stellar spectral type along with the blackbody continuum. Sorry, the blackbody UV continuum. But it turns out that when we look at the shapes of the Lyman alpha emission lines in the Ulysses spectra, we see quite a large spread, right? These are very rarely symmetric Gaussian line wings. And so on the y-axis here, I'm plotting the ratio of Lyman alpha flux on the red side of the line to the ratio on the blue side of the line. And this dashed line here marks off where the profile would be symmetric. So even emission at plus or minus 0 kilometers per second. And for the most part, our disks show kind of what we expected to see. Absorbed on the red side of the line by, or sorry, on the blue side of the line by outflowing. But we also see this very interesting population down here where the opposite type of profile is more emission. Or inverse profiles, kind of like an inverse. So this is very interesting, right? Because the T-Tauri stars that were included in the Ulysses program do not span a huge range of spectral type compared to the models that we were looking at earlier, right? So predominantly, we still see this spread in the shape of the emission. And it turns out that when we compare the shapes of these emission lines to the properties of the protoplanetary dust disks and the properties of jets and winds, we see a really interesting. So this have smoother dust disks. They also have really strong signatures of high velocity jets in their emission. They also have really strong signatures. All of the freedom alpha is really going to. But the other interesting thing is that when we look at the targets, opposite behaviors, we're all seen in disks that have signs of dust structure. So these are disks that don't show high velocity emission. So it seems like we need to take the UV radiation field into account along with the dust substructure. Talked a lot about the dust. Turns out that similar trends are population two emission lines that are pumped by the Lyman alpha. We've seen a couple of really nice spectra of H2 emission lines. Thin, hot surface layer of gas in the absorbs Lyman alpha and pumps cascade of emission lines. And because these emission lines are spectrally resolved, if we assume that the disk is in Keplerian rotation, we can use the width of the emission line to calculate an average radius of where the H2 y-axis of both panels, we're looking at that inferred Keplerian radius. And we find that our trends here again between the H2 emission, gas in the inner disk, dust that we chapter, general trend further away from this. And if we look at the photometry from Y, so we're looking, so this is 12 minus 24 micron colors, see that disks with larger Y's colors, relatively less emission at 12 microns that also have. So whatever is happening to the Lyman alpha seems to be happening in unison with the dust disk evolution. Seems to be reflecting what is seen by the very hot gas in the disk. So if we try to then back out what the radiation field itself would look like for this gas in the disk, I'm talking a lot about the wings that we've contaminated. Why would, well, if we use these H2 emission lines, reconstruct what's happening with the Lyman alpha at the surface of that very hot gas layer, we see some very interesting things. So this is a Lyman alpha reconstruction. Black here is our model Lyman alpha spectrum of these red points. And if we take this reconstructed Lyman alpha profile and integrate the area under the curve, compare that to the total FUV continuum, find that the Lyman alpha line in this disk actually only makes up about 25% of the total. Remember, those models I showed you earlier were assuming that it always makes up. So it's quite possible that you're over-predicting how much So to think about the other molecules, my student Carlos Ortiz took all of those Ulysses disks, kind of blue-shifted Lyman alpha, all dust cavities. He reconstructed the Lyman alpha line profile. The idea was to zoom in on one population with dust. He wanted to see what the Lyman alpha was doing. Y-axis here, we're looking at the total amount of photodissipation at wavelengths corresponding to water, methane, and ammonia, and CH. And so you can see that again, even in this population of K and M type stars that have very similar dust disks, we have a spread of about 2 orders of magnitude in the amount of photodissociating Lyman alpha radiation into that innermost. So this is, again, we really need to have observations of the UV to understand what's happening. Now, keep in mind that because these Lyman alpha reconstructions are done based on the H2, really about the photodissociating flux, hot, thin surface. And Chang later today is going to tell us propagation of Lyman alpha. We can see what this right at the very surface. Photons can scatter down close to the disk midplane and to get further out in radius, and we'll hear that later. Now it turns out that I showed that figure where we signatures of jets. Turns out that the structure of these but it can be very challenging to get direct constraints on the properties of these emission lines. And so, in some very special cases, we can actually use observations with the MIRI MRS and get some constraints on the. So these 4 images are from MIRI observations of an edge-on disk in Taurus. Actually was just accepted as of midnight. We're very excited about that. But in each of these 4 panels, the white contours are showing the magma color map in the top left panel is showing the sub-millimeter dust continuum at. On the right-hand side, we're looking at emission from the beautiful extended structure. Fortunately, with the MIRI MRS cubes, we can't quite resolve the inner launching radius. So the opening angle of this is very consistent with. Down in the bottom here, we can see a very nice jet-like distribution of neon 2. And on the right-hand panel, we can see a little bit of scattered light from the hydrogen-Humphreys alpha transition, scattering up into upper layers of the disk. This is also kind of a cautionary tale, right? Very little of the total Humphreys alpha. So for edge-on disks, all of those correlations between the hydrogen lines and the accretion. Okay, so I will leave you with just a few things looking forward. It feels very selfish to be standing here during this conference presenting a beautiful public archive, but we do need to. We don't have very many observations at the lowest mass, highest. Well, I shouldn't say the highest, at the lower and the higher mass ends here. So we have maybe a few representative M dwarfs and Herbig stars, and again, it seems like we can't really read this. People in this room are doing a lot of work to push to better understand brown dwarfs and planetary mass companions, and this will really help us understand. We also really need to support more theoretical work that can incorporate really beautiful of the CFA. Jenny found the chemistry of the disk actually changes over time, moving from an X-ray dominated to a UV dominated chemistry. And again, I think as Carlo mentioned, we need to understand better how the UV. Well, I'll leave it at that. Thank you so much to the implementation team for having me and for all of your work over the last few years. Happy to take any questions.
Questions for Nicole?
So excellent stuff, Nicole. I have 2 questions. So one is on the chemistry. So so you said also here how the UV field changes over disk lifetime, but there is also a lot of variability. I mean, short-term variability. Do we have an idea of how this impacts the chemistry?
So we're starting to be able to poke in that direction. So Parker Hinton had a nice weird where he looked at spectra, really broke it down to look for variability in carbon-4, a few of the other accretion tracers. The thing that I was most excited about from that paper was actually that he was looking at variability. And I think this is something that we'll be able to do with really nice. That will be really awesome. And actually, for JWST Cycle 3, we're going to get some nice. There were 2 separate programs that were approved now. Binary that's known to have variable accretion. And so their goal is to monitor how the water emission changes time, and they'll hope water very slowly.
And can I ask another one? Yeah. Okay. So the Neon 2, can you go back to the nice image? So the so my understanding has always been that the Neon 2 was from more a disk wind than an outflow. I mean, the velocity was low. That's a jet. I mean, it's very narrow. So do you think this changes a little bit the way we look at this line?
So I think it depends on the system. So Uma showed yesterday this nice image of T. And so T-Cha, the spatially resolved Neon 2, does look more velocity. It's possible that this is this. It's very hard to resolve substrate. It's quite possible that this is a more smooth disk distribution, and so then the higher velocity. We definitely don't see any overlap with the extended. But I think it depends on the disk. Observations are the system for a long time. Awesome, I think. Sub-millimeter dust properties.
Okay, I think we have time for one more question.
I can just say that right now. The Neon 2
The comment for anybody online is that the Neon 2 can also come from shocks. All right, let's thank Nicole again. And next up we have James Owen.
Right. Good morning, everyone. It's a great pleasure to be here as the sole representative of the exoplanet community. And what I'm going to do today is talk about why the impact of UV irradiation, particularly from young stars, is extremely important for interpreting the exoplanet population that we've discovered. So one of the key important facts about the exoplanet population that we discovered is, one, there are more planets than stars. Two, most of those planets are extremely close to their host star, inside the orbit of Mercury. In fact, the most typical orbital separation for a planet is about 0.1 AU that we've discovered today. And these planets are of an unusual type. They have a size in between Earth and Neptune. We have no analog in our solar system, so we don't really know what they are made of, but we know that many have volatile, rich atmospheres, some of which contain lots of hydrogen and helium. So if you have a planet that is extremely close to its host star with lots of hydrogen and helium, it's going to be extremely vulnerable to the effects of UV radiation. And as everyone in this room knows, UV irradiation is much more important when the stars are young, particularly during the T-Tauri phase. And the majority of the exoplanet population we've discovered is billions of years old. So we need to understand how planets evolve from when they are born into the population we see today in order to interpret observations of their atmospheres, which is now the big growing field in the exoplanet community. The final thing is, even though the exoplanet population is billions of years old, there's very, very strong lines of evidence that that planet population has been there since disk dispersal. There's two reasons for this. One is, I said most stars have planets, and there are more planets than stars, so this means that most planets are in multi-planet systems. And it's basically impossible to construct any kind of dynamical scenario where you can move planets from large separations to small separations without a disk. The second is that we've now been successful in actually finding multi-planet systems very, very close to their stars at very young ages. In fact, the youngest multi-planet system is about 12 million years old, around V1298 tau. So what I'm going to do is I'm going to talk about, I also didn't get the memo to show to Lee's picture, so I chose this one. I'm going to talk about the two impacts of UV radiation on close-in planets during their early lifetimes. The first is going to be what I talk about, sort of an indirect implication. So in this sort of diagram here, this is difficult to get used to. I understand why people have been having such a challenge. You have a evolving protoplanetary disk here, and the UV radiation is driving winds from these disks, and these winds are driving disk dispersal. Now, the planet is sort of in the wrong location in this cartoon. You can think of it as more being here. Right, so the fact that a planet exists in a disk during disk dispersal has a big impact on that planet's evolution, and I'll show that. And later, when we go on, we have the direct impact of UV radiation on our planet, so that you have a planet sitting about here being absolutely blasted by the UV radiation, heating up its atmosphere and driving a process called atmospheric escape. So what I'm really going to talk about is a tale of mass loss. Planets cannot, when they're close to their stars, cannot hold on to mass over their lifetimes. So the first impact comes from this indirect process of simply the fact that planets are close to their stars during disk dispersal. So UV radiation is driving these winds that we heard about from Uma, and what these winds do is they drive rapid inner disk dispersal. So early on in the disk lifetime, these winds typically have mass loss rates less than the accretion rate, so the disk behaves as if the wind isn't there. But as time goes on, the accretion rate drops, the wind gets more significant, and you start starving the inner regions of these protoplanetary disks of resupply from the outside. Material is preferentially being lost in the wind. Eventually, you get to the point where the wind is more powerful than the accretion, and you rapidly disperse the inner disk. So you get a rapid drop in surface density. Now, imagine you're a planet. You're extremely close to your host star, and you're surrounded by this lovely protective protoplanetary disk, and your atmosphere is in hydrostatic equilibrium with this disk. You've been sat there for a few million years, forming on a few million year timescale, so you're going to have a cooling timescale of something like 1 million years. This is basically the timescale on which you can respond to changes. But I have rapid disk dispersal. So rapid disk dispersal rapidly removes the inner disk on a timescale much shorter than this million-year timescale. The planet is extremely unhappy. It's a lot like ripping bed covers off people you don't like. You were in hydrostatic equilibrium with a pressure-confining environment that you've rapidly removed, right? So the atmosphere expands, and it starts to throw off initial mass that it's accreted. And this process we've coined or called boil-off. So the physics of what's going on here is you have a planet that can't respond to this change in boundary conditions, so it's expanding and throwing off mass. It's being heated not from the star at this point, because it's still surrounded by the disk. It's actually being heated from its interior, and this is the energy source for driving this outflow. So as you drive this outflow and you cool, you shrink in the interior. And what happens is, as you shrink, the planet's atmosphere gets deeper and deeper and deeper into the gravitational potential well of this planet, and it gets harder and harder and harder to throw off more and more atmosphere. And eventually, the mass loss timescale of this process grows longer than essentially the age of the universe. So you sort of rapidly shut off this process when the planet gets quite small. So the planet radius has sort of about a tenth of the radius of the sonic point of this outflow. So this is really dramatic, actually. In fact, planets lose most of the mass they initially accreted during this process. Up to 90% of the mass they initially accreted, they lose during this boil-off process. So you can see these are different accretion curves. So this is time on the x-axis. I've lost my cursor. This is time prior to disk dispersal on the x-axis here, and this is time after disk dispersal here. What you can see is planets initially accrete, there it is. Planets initially accrete gas, and then at disk dispersal, they start going through this boil-off process, and they dramatically lose a lot of mass. And they're sort of shepherded towards having a few percent by mass weight atmospheres. So typically, they accrete 10s to 20%, these low-mass planets, but they end up with 1% after this. I think one of the most interesting impacts is you can see these different lines started the planets forming at different times. But the different styles refer to different disk dispersal timescales. So a sort of one expectation is if you've been accreting for longer, you should end up with more mass, which you see is true prior to disk dispersal. But this boil-off process actually wipes out any effect of this. In fact, the thing that's setting the properties of the planet's atmosphere after disk dispersal is actually the disk dispersal timescale. So understanding how disk dispersal happens is really critical to understanding and setting the initial properties of planetary atmospheres. So disk dispersal is more important than formation time. So now the disk is gone, and we have a planet that's directly exposed to the star's spectrum. So we have the high energy radiation that's sufficiently energetic to dissociate molecules in the planet's atmosphere. And we have the even higher energy photons that are sufficiently energetic to ionize atoms. The UV is really easily absorbed, has a very high cross-section. X-ray and FUV have a bit lower cross-section. They penetrate a bit deeper, and then the sort of visible that most exoplanet people care about goes way deep into the atmosphere. So in terms of the sort of structure of the planet's atmosphere, you have initially an EUV heated layer, then you have an X-ray / FUV heated layer, and then you have a bolometrically heated layer from the star. So in terms of the properties, you have an ionized layer, an atomic layer, and a molecular layer. And this is really important because ions and atoms are really crappy coolants compared to molecules. So this upper region of these atmospheres ends up extremely hot, up to 10,000 Kelvin. The physics is exactly the same as disk photoevaporation. So what happens is exactly like disk photoevaporation. This atmosphere is too hot to be bound, and it escapes away into space. And planets lose atmospheres over their lifetimes. What you can do is you can use simulations to compute mass loss rates as a function of planetary parameters. I'm going to draw your attention to one line here, which is these two thin dotted lines here. These are mass loss rates times a fixed time, so basically an estimate of the total amount of mass you could lose over some period of time. So if you're very, very close to the left, and just to the left of these dotted lines, you're extremely vulnerable to this process. If the planets were way to the right of this line, we would have done something wrong, which we haven't. So you can see, you can see that it is the sort of these common low-mass planets that are extremely vulnerable to this process. Now, when is mass loss important? These planets are billions of years old, but because the X-ray and UV emission from host stars is dominant when the stars are very young in the T-Tauri phase, if you integrate it up and you ask when is most of the energy absorbed, it's absorbed within the first 10 to 100 million years of the planet's lifetime. So most of the action of this heating and mass loss happens within the first 10 to 100 million years of the star's lifetime. Hot Jupiters, they're close to their stars, they're highly irradiated, they also lose mass, but they don't really change, Right? There's two reasons for this. One, they have a lot of mass to start with, so you can afford to lose quite a bit. And the second is hot Jupiters have deep gravitational potential wells, so it's hard to drive efficient outflows. Whereas for these more common, smaller and less massive sub-Neptune and super-Earth-style planets, you can strongly affect their evolution. And you can see, again, most of the action is happening within the first few tens of millions of years of the planet's and stars' lifetime because of the bright UV emission. So do we have any evidence that this is happening in the exoplanet population? And you can look at the exoplanet population, you can see a few anomalies, right? So the exoplanet population is really old. And one of the first systems that sort of caught an eye was this Kepler-36 system. It has two planets in very, very tight in orbits. The orbits are not actually that far apart. So one's about 0.1 AU and one's about 0.12 AU. But the low mass planet is basically a terrestrial planet, and the more massive planet has a thick hydrogen-helium atmosphere. So it was a struggle for planet formation theorists to come up with an idea of how it might form like this. It wasn't so much of a challenge that they couldn't come up with scenarios, planet formation being so uncertain. But a more natural scenario is perhaps that this planet, because it's less massive, started off with a hydrogen-helium atmosphere, and its weaker gravities meant it wasn't able to hold on to its atmosphere and actually lost it over time. So this is kind of the evolutionary scenarios we might expect for these planets, that the innermost planet, which had a lower mass, was able to be completely stripped of its atmosphere, while the outermost planet was able to retain its atmosphere. And again, you can see almost all the action is happening within the first few tens of millions of years of the star's lifetime. So you can ask an even larger question. Well, in this system, I can explain its properties by all planets hosting an initial hydrogen-helium atmosphere, which one then lost. What happens if the majority of close exoplanets hosted hydrogen-helium atmospheres when they were born? What would then happen? Right, so you can imagine that you have a population of planets that have a solid interior, a rocky interior surrounded by a hydrogen-helium atmosphere, and you put them very, very close to their stars. And what happens is the planets really, really close to their host stars, they lose their atmospheres. Planets with weak gravities, they lose their atmospheres. But planets with large cores, strong gravities that are far enough away from their star are able to hold on to their atmosphere. And what started off as an initial singular population evolves over the first tens to 100 million years of the star's lifetime into two populations of distinct planets. So you have planets with about 1% of their mass in a hydrogen-helium atmosphere, and you have planets that have been completely stripped. And this population looks remarkably like the observed exoplanet population, where we do see these two distinct populations. Bit of physics as to why this happens, right? Why do you get two populations from a fairly continuous process? So what you can think of is basically how long can you hold on to your atmosphere to this mass loss process? Mass loss is essentially governed in the simplest way by how much high energy radiation you can absorb from the star, so basically how big you are. So what happens is as you increase your envelope mass, your mass in your atmosphere, you're getting larger and larger and larger, so you can absorb more UV radiation from the star and drive stronger mass loss. But as you're also adding envelope mass, you're adding more mass that you have to lose to start with. Right? So there's a competition between these two effects. When the envelope mass is very small, most of the radius in the planet is set not by the radius of this atmosphere you're adding, but the radius of this interior rocky core. So as you add a little bit more mass, you haven't changed the radius of the planet very much. So you haven't changed your mass loss rate, but you have changed the amount of atmosphere mass you have to lose. So your mass loss timescale starts increasing. By the time you get to the point where the envelope mass is starting to dominate the radius of the planet, these planets expand so rapidly that the mass loss rate grows up dramatically and the mass loss timescale comes back down. So as you add envelope mass, your mass loss time gets longer and longer. Then you reach the point where the envelope dominates the radius of the planet, and the mass loss timescale comes back down. So you end up with something like this. And now you have your tens to 100 million years of action from the star where you can drive these powerful outflows. So if your mass loss timescale is less than this, then you're unstable to mass loss. And if you start off over here, right, you can undergo runaway stripping. But if you start off here, you start losing mass. You're moving in this direction along the x-axis, but your mass loss timescale gets longer and longer and longer, and you can evaporate up to safety. So we now have a well-characterized atmosphere exoplanet population. So you want to ask, what did this billion-year-old exoplanet population we see look like after disk dispersal? Right, because you've had lots and lots of mass loss that's been going on. So what you can do is you can take a guess at what you think the initial population was. You can evolve them through this process. Then you can observe them with something like Kepler. And then you can produce a synthetic guess at what the billion-year-old population looks like, and you can compare it to the observed population. You would say this was a bad guess. The nice thing is, right, you can combine this whole thing into sort of an inference problem and then adjust your initial guess. And you can show that you can get a perfect match to the exoplanet distribution. So this is some work by my former PhD student, James Rogers. And what he showed is that even though we see two types of planets today, close to their stars, terrestrial planets and planets with thin hydrogen-helium atmospheres, they actually nearly form through a completely uniform channel where they all started off with hydrogen-helium atmospheres. So this is the initial distribution of envelope masses peaking at a few percent. And then this is the final distribution. So we have a small fraction of what I think of as born terrestrial planets, or sort of solar system terrestrial analogs, but most of the terrestrial exoplanets we've discovered were actually evaporated into terrestrial planets. They've lost their atmospheres, they accreted. You'll see that this peaks at a few percent rather than 10%, which is where core accretion would put you. And rather remarkably, if you plot what the initial distribution of envelope mass as a function of core mass should look like, this is where core accretion should put you on this line here. And this is where you would get if you started on core accretion and went through this boil-off process where there's disk dispersal. So the whole picture actually quite nicely hangs together. Where are we going with this? And what are the leading order questions? And also, why is accurate UV spectra really critical to where we're going in this field? So as we're starting to interrogate these planets' atmospheres with JWST, we want to know what their detailed compositions are, right? So as I've described this whole mass loss process before, I've been very vague as to what's being lost, right? Is it just the whole atmosphere in some sort of uniform mixed composition, or does the composition evolve? Right, and you can ask sort of very simple questions. Does the metallicity and heavy element ratios in planets that retain their atmospheres evolve? And can we retain any small amount of hydrogen in these terrestrial analogs? And this is where a process called heavy element fractionation comes in, which is if you have a very strong hydrodynamic outflow, collisions between light elements like hydrogen and heavier elements are very efficient, and the whole thing just happens in a coupled fashion. However, if the outflow is a bit weaker or less dense, then those collisions are not as efficient, and heavy elements sink into the atmospheres. And you would retain heavy elements and just lose the light species like hydrogen. And you can get an in-between process where you sort of lose the heavy elements, but not at a 100% efficiency. Now, this process has been well known. It's been studied in the solar system, and it's actually been solved. It's been solved by theorists, but it's been solved by theorists in theorists' units, which are dimensionless units. And dimensionless units are not useful for real calculations, unfortunately. So what we have to do is simulate this process. And it's very complicated because these collisions critically depend on the ionization states of the heavy elements, and the ionization states of the elements critically depend on the UV spectrum. So one example we've been exploring so far is because carbon is easier to ionize and the FUV flux is higher than the EUV flux, we expect stronger evolution and stronger coupling of carbon and oxygen. And also the metals are really important for cooling, so if you start dragging out the metals, they start cooling the outflows, which makes the dragging out very efficient, less efficient. So there's this interesting feedback loop that can happen. So my postdoc, Mateus, has been simulating this process. Nice video, just for fun. The real thing is the various mass loss rates of not just hydrogen, but all the different species. And what you can see is they're not just nice, simple, uniform lines, they're actually very, very complicated. So things like the C to O ratio, which if you talk to any exoplanet atmosphere person in this room, they are not in this room, but in this building, they are desperate to measure, right? But it's going to evolve, and it can evolve significantly, and you're going to build up heavy elements in these atmospheres. So some example styles of evolution is you can lose hydrogen efficiently first, then you couple the metals in, and you can end up with a carbon-oxygen dominated atmosphere first, and then because you lose the carbon more efficiently, you can end up with just an oxygen dominated atmosphere. So you get an increase in metallicity of the atmosphere, or if you retain your atmosphere to long ages, you can get a very heavy element-dominated atmosphere that, even though you started off with equal amounts of carbon and oxygen, you can deplete the carbon very efficiently and end up with an oxygen-dominated atmosphere. This is just the early stages of this. It's going to be far more complicated than these real pictures because you can replenish the atmosphere from inside the planet. So that's not in these models. So that's the future work, and that's why we're interested in sort of accurate UV spectra for calculating the impact on these outflows in a detailed way. So what should you take home? Well, young stars are really important for the early evolution of close-in planets, and close-in planets are everywhere. The first phase is this boil-off phase driven by rapid disk dispersal. It's sort of the impact of UV radiation on the disk drives impact on the planets, and then when the disk is gone, you blast away the atmosphere directly with the UV radiation. And this process can and will change the composition of the exoplanet's atmospheres. This is the future. I don't know the answer to it yet, but we're working on it. Thanks very much.
Questions?
Yeah, thank you. Very nice. I have a question about, so since you mentioned that the change in mass for the planets when they get boiled off, when they're very close in, can be quite dramatic, like 90%. Since they are losing mass quite rapidly, could they be in this way forced outwards by losing mass that by conservation of angular momentum they would have to be migrated out?
So I don't think it's specifically clear that they have to migrate outwards because the wind is so efficient that it's not sort of a classic Roche lobe overflow where you all go through L1 and then you have to go out, right? The wind expands spherically and can go out of both ways. I think the impact on the migration of the planet is unclear at the moment. So we're trying to construct Fargo simulations where you couple these interior evolution models to the disk evolution and find out which way you're going to make the planet move, whether you move inwards, outwards, right? And all these planets are also in really tightly packed multi-planet systems. So if you move one planet a little bit, you affect all other planets as well.
Yeah, as a follow-up, very short question. So the effect is essentially that the disk is dispersing quite rapidly, but does this happen in all the disks, or are these, because I don't really know, are there disks that they disperse less rapidly, others more rapidly?
Yeah, so sort of as I showed in that plot, the disk dispersal timescale critically sets how much atmosphere you lose. So, and obviously if you change the sort of the UV properties or the X-ray properties of the star, you will change the properties of the winds driven by the star, and you'll change the disk dispersal process, and then you'll change how efficient this is. Essentially, the key timescales is the ratio between the cooling time of the planet and the disk dispersal timescale. So if you make the disk dispersal timescale longer, you make this process much less efficient, which you can see here, that the longer disk dispersal timescales, they lose less mass. So, and if you make disk dispersal so long that it's slower than the cooling timescale, then the planets will just keep everything.
Thank you. I see there's a question online. Greg, go ahead.
Hi, Greg.
Hey, James. This is Greg Herzig. Thanks a lot for a really beautiful talk. I had a question on the observational uncertainties and what they are and whether there's anything the observers can do about it. And that for most of this conference, we've been talking about the accretors, but once you lose a disk, we don't have the messy issues. And so do you feel like the UV and X-ray fields are well enough known? Or do you think that there are kind of gaps in that knowledge that we should fill? Thanks.
So, yeah, so the real critical things, I think, are understanding the spread in what the UV emission is around the photoionization edges of key species like carbon, oxygen, magnesium, silicon. Sort of, because at the moment all these calculations are done just assuming a mean spectrum, right? But we know that there's a real spread, and we're comparing to a population that has a spread. And the thing that also is very important, but I know is very, very hard for observers, is the EUV spectrum, and particularly the soft EUV spectrum around 13.6 eV is particularly critical to this process, but that's hard to observe. So any observations that can help better reconstructions of what the soft EUV field will be is also very, very critical to this process. There's this sort of interesting historical perspective of someone who's also worked in disk dispersal and photoevaporation. There's been this large debate that's still going on. Is it FUV, X-ray, or EUV-driven photoevaporation? And that's because it's a technical challenge to simulate this process in disks. In planets, it's much easier. We do it all. And you get this sort of phase of X-ray to FUV to EUV-driven outflows. And understanding, again, the spread in how that happens is going to be critical to understanding what the overall population looks like.
Okay, let's thank James again. And now we're going to hear from Karina Malko. Discs again.
Thank you. Yeah. So can all hear me okay? Okay, well, first of all, thanks to the organizers to give me the opportunity to give this talk today. I'm a postdoc at ISO Garhin, working with Carlo Monara and Justin in the ERC Wanda group. And today I mainly want to talk about photooperation of disks from UV radiation emitted by T-Tauri stars. So first of all, the motivation of this talk, we've been hearing a lot of reasons why the UV is important for characterizing these inner parts of a disk, and we know that disks are evolving in time because they are accreting material from the disk to the stars, and we know that these also produce these collimated jets that have been widely observed with different tracers of emissions lines. But we also know that these lose mass, so they disperse mass through winds. And the winds in the protoplanetary disk comes in different flavors. We have the magnetodynamical winds that have gained a lot of attention lately as a driver of accretion, because we know that MRI is mainly inefficient in a lot of part of the disks. But also we do have the thermal winds, so the photooperating winds produced by the emission of the UV and also X-ray from the central star. So if we want to really understand the evolution of disks, we really need to characterize these dispersal mechanisms in the disk, so the winds. So we know that from the Ulysses sample in the UV, we can have a very good understanding of the chemical part, the molecular part in the inner disk, as we were seeing from these last couple of days. And Nicole also talked a lot about the special distribution of the major gas phase constituents thanks to this part of the UV spectrum. We also have chemical abundances and excitation in this really inner part of the disk where planets form, so it's very important to also know about this. But I believe that one of the game changers in this Ulysses sample is how that connect with other surveys, like for instance the Penelope survey, which is a continuous or almost simultaneous observations that also goes from the optical and from the infrared. So if we combine these two data sets, we can also characterize not only the molecular component, but also the atomic component in the protoplanetary disk, and we can also have access to all these wind and outflow tracers from the forbidden lines. That is also something that I'm gonna talk a lot about in this work. And also going even further, we can also go to longer wavelengths, so to millimeter observations with ALMA, and we can really start looking at the connections between the inner disk and the outer disk. And I think that's where the legacy of Ulysses is going to be really strong. So the bottom line is that we need to determine the properties of the disk wind because it's a fundamental step in trying to understand the evolution of protoplanetary disks and also planet formation. So the role of the UV irradiation from the central star to the disk, we already heard about this from Nicole a couple of minutes ago. We know that from the Ulysses, we have all these, a lot of information of the UV driving chemistry in the system by looking at the H2 and CO fluorescence emission. Also, we also heard how the shape of the Lyman alpha profiles can also is linked to this structure in the systems. So we know that having all this information in the UV can give us a general view of the system where the UV radiation fields, the disk winds, jets, and the molecular component of the disk seems to be evolving in harmony in this system. So it's very important to have this. But what I really wanted to point it out here today is how the synergy with Ulysses in the Penelope observations can really be a game changer in this respect. So in this recent work from Manuel Ganji in 2023, what we did was took the Orion observation, so these are Orion targets, 11 targets in Orion, and what he did was simultaneously study the H2 lines from COS, from Hubble, and also the optical emission lines, in this case the oxygen 1 at 6300 and different forbidden lines in the optical, and he simultaneously fit these lines with different Gaussian components. So as you can see, we identify like the typical high velocity component of these sources, which is related to the jets, but also the low velocity component with the narrow and the broad component. And really what we wanted to tackle in this work was really the origin of this low velocity component. So one of the questions that we wanted to answer in this paper was what is the excitation mechanism of the oxygen 1 low velocity component? And that is very important because the fundamental step in trying to estimate the mass loss rate, which is the crucial parameter here in order to know the lifetime of the disks, is to characterize the emitting gas, so the temperature and the density of the gas. And we do that by using line ratios of these forbidden emission lines. But we can only do that if we assume that the lines are thermally excited, so collision excitation of the oxygen 1 line. But we also know that FUV photons can also produce a non-thermal contribution of this line by via of photodissociation of OH Also FUV pumping, as Nicole was also talking about. So it's very important to really establish if this line is being thermally excited or not, and that's when the Ulysses observations, simultaneous observations in the UV really comes very handy, because we can really now start to looking at these emission lines and really see if this line is thermally excited or have a non-thermal contribution. So that's what we did in this work as well, and this is the main result of this work by Manuel. This is the sketch of the system that we found given these observations. And one cool thing that we can do, as Nicole was also saying, is that if you use the width of the lines that you fit and you assume Keplerian broadening, then you can estimate the region of the emission of the lines, where the lines are coming from. And as you can see here, very interesting, what we found is that H2 emission from the UV is overlapping partially with the narrow low velocity component of the oxygen one, as you can see here. And this scenario is consistent with the FUV that is producing the H2 line having a significant contribution in the excitation of the oxygen one narrow component. So that is something that you have to be taken into account when you study this type of tracers in winds in these systems. And also, there was also seen in the larger spread that we found from the line ratios that also points to a non-thermal contribution. And that is just because we have also these simultaneous UV observations with Ulysses. So that's, this work shows the potential of having these multi-wavelength observations and try to link these different tracers in protoplanetary disks. Of course, this is a work done from the UV and the optical, but it's not the first work that is tackled this oxygen one line as a tracer of winds. We now have decades of studies with different papers that have also been working with this oxygen line in the optical. And the main question here that is still an open question is where is the line is coming from? Is coming from a magnetodynamical wind in the inner disks, or is coming from a thermal wind, a photoevaporating winds? So what we know about this line thanks to all this work? Well, there's a general consensus that the high velocity components observed in the oxygen one line is definitely coming from a jet, so a collimated jet at hundreds of kilometers per second here. But for the low velocity component, it's a little bit tricky. There seems to be more and more a consensus that the broad component of this line traces hot dense gas close to the base of a magnetodynamical wind. So have this origin of the magnetodynamical wind. And actually, Basanti 2019 also argued that the entire low velocity component, so broad component and narrow components, might be tracing a radially extended magnetodynamical wind. And he based this conclusion in the fact that they found that the kinematic components of the broad component correlates with the narrow component and also with the high velocity equivalent width, which is also something that Uma mentioned. So you can see that it seems to be like this broad and narrow component of the oxygen one line is tracing a similar thing, the magnetic aerodynamical wind. But however, Weber, in a more recent work, he understands these correlations by just simply saying that the line luminosity seems to always correlate with the luminosity accretion. And actually, these optical forbidden lines are best reproduced by a combination of a magnetodynamical wind, which is proving the high velocity and the broad component, plus a photoevaporating wind, which is related to the narrow component. So as you can see, we are still don't know what is the origin of the narrow component of this oxygen one line. We know that the high velocity and the broad components seems to be related to the magnetodynamical wind, but we still need more observations and probably new techniques to try to understand the origin of this narrow component. As pointed out in Whelan 2021 with spectroastrometry techniques, at least for one source, RU loop, we know for sure that the narrow component seems to be related to magnetodynamical winds. So this is something that we are still working on, and hopefully with future observations, we can really understand what is the origin of this narrow component. But this is only using the optical observations. So something that we can also do is go to longer wavelengths, so the infrared, and go to the neon 2 lines that Nicole was also talking about at 12.8 microns. This line has also been widely studied. It's also tracing a slow thermal wind, and there's a lot of efforts in this line in works with Pascucci and collaboration. And as Nicole was saying, in this recent paper from Pascucci, what they found is very interesting because they link the optical oxygen 1 line and the infrared line, the neon 2 line, in a set of discs with full discs and with cavities. And what they found is that the discs with cavities do seems to produce or to have the low velocity component of the neon 2 line. And that's something that you cannot find in the full discs. So how do you explain this? Well, what they explain is that for the full discs, you have a strong emission in the oxygen 1 line. They related this to a magnetodynamical wind that is blocking the hard X-ray emission, so the X-ray cannot go to the outer disc and photoionize the neon 2. And that is something that can happen when you have an inner cavity. So the magnetodynamical wind traced by the oxygen 1 is is weaker. So the hardest ray can pass through the wind and ionize the neon 2. So you can see that you expect to have different emissions of the oxygen 1 line and the neon line if you have a dust cavity. So you expect a change in the oxygen 1 with the cavity. And this is also confirmed and demonstrated by this recent work from Baja. This is actually 2024 because it's like a couple of weeks back. They observed this T-CHA that Nicole was talking about with JWST, and they actually resolved the neon 2 line, and they confirmed that this wind is actually coming from the outer part, and it's a thermal wind. But they also detected, in these very new results, argon lines in a protoplanetary disk. So you can see now that with JWST, we can really start to look at this structure of the winds in this like onion shell wind, where you have the argon lines in the inner parts and produced by the EUV. But then this wind traced by the argon is blocking the UV, and now the X-ray is the only one that can ionize the neon. So you can see that having all these multi-wavelength observations can really give you a hint of what is happening in this system and how they loosen material through these winds. So that is very, very interesting. So you expect to have different behaviors of the lines with a dust structure. And that is also something that have been pointed out in the past. So we have this work from Ercolano and Pascucci in 2017, this plot that also James was telling us about. And you can see that if you have the oxygen 1 line for a full disk, so you expect to have the narrow and the broad component. The broad component is coming from the inner disk. And while the disk evolve and you start carving a cavity in the disk, then you lose the broad component and you only end up with a single component of the oxygen 1 line. So you can see that this is a great way of connecting the inner disk with the spectroscopy and the outer disk with, for instance, radio observations and ALMA. And that is also something pointed out by Basanti 2019, where they found that if you have a cavity in the disk, then you lose the high velocity component, you lose the broad component, and you end up with a single component in the oxygen 1. So you can really start to looking at this oxygen 1 line and trace the evolution of the dust as well. And that is also something that Justin talked about yesterday with the oxygen 1 profile of DS70. So you expect that if the line is changing with the dust cavity, you also expect that they change with age, because we know that for the later stages, internal photooperations, so this inside-out dispersal of the disk, will also be more prominent for older regions. So you also expect that the oxygen 1 line change with age. And that's been some efforts from these papers here and try to observe this oxygen 1 line in different regions with different ages. So here I show you the kinematic behavior of the oxygen 1 line, so the full width at maximum, as a function of the peak velocity, just as Justin was also showing yesterday, for the oxygen 1 line for 3 different regions with different ages. And you can see, as predicted also in the previous work, that while the disks or the populations evolve with time, you lose first the high velocity component, which is green symbols here. You see that upper Scorpion here, this is about 5 to 10 million years, doesn't really have any high velocity component. And also the broad component, which is the purple symbols here, also they're barely seen in upper Scorpion, and you end up with a lot of single component lines. So what you expect with this evolution with time is that the high velocity component and the broad component start to disappear, and you end up with a single component, which become the dominant mode in other regions. And just as highlighted by Bruxelles and Nicini last year, you also need to take into account that while the populations evolve with time, you also starting to have more contribution of the disemission in the forbidden lines. So it's very cool that we can start looking through a spectroscopy to these optical forbidden lines, try to see the effects of age in these protoplanetary disks. So in this sense, all of this work have been done in low mass star-forming regions that doesn't have massive stars, but we know that the majority of the stars and planets, planetary systems, form in massive environments where the feedback from massive stars can really impact the evolution of the disk. So in that sense, our work that we're currently working on is very useful because we are working in this young cluster, which is intermediate age, so 3 to 5 million years in Orion, so it's the Sigma Orionis cluster, that we know that at the center of the cluster there is this massive OB system, Sigma Ori, that it seems to be affecting the disk close to this massive star by externally photoevaporating them. So the FUV radiation from this massive star is affecting the disk and is clearing the disk from the outside in. So here I show you just the spatial distribution of our targets. So Sigma Orioni is here, Sigma Ori is here in the center, and we studied this cluster in this paper from last year. We observed this cluster with ALMA observation, so we can have the dis-dos mass of our sample. And if you compare the dis-dos mass versus the projective separation from the massive star, so the inner parts here, as you can see, really are composed of targets with very low masses, which is an indication of external photoevaporation. And you can see this increasing trend of those masses with projected separation that also indicates an environmental effects in this cluster. And this particular cluster is very interesting because you can study the external photoevaporation, so the feedback of the massive star here, but at the outer parts, as you can see here, we have a wide range of masses. We can even have a lot of 12 CO detections here. So you can, at the outer parts of the cluster, you can really start looking at the evolutionary stage because it's an intermediate age cluster. But at the center, you can really just study external photoevaporation. So that is very cool. So what we did now was try to characterize the protoplanetary disk here by looking at the oxygen 1 forbidden line. So we observed this cluster with Mike in Las Campanas Observatory. Is high resolution spectrograph in the optical. And what we did was study the oxygen 1 line. So we basically fit the forbidden lines of all the detected sources. And we decompose these using multiple Gaussian components as what is usually done in this case. And now here I show you the kinematic behavior of the oxygen 1 line for Sigma Orionis. So you can see again the full width at maximum of the line versus the peak velocity. And you can see that we have sources with narrow and broad components, but also single components. But what is very interesting in what you start looking or comparing this with younger and older regions. So here I show you the comparison with Basanti 2019. So it's younger region, 1 to 2 million years. You can see that more or less they seems to be agreeing. But then what is really striking is when you start comparing with older regions. So you can see clearly how they very different. They lose the broad component, and then you start getting just single components. And this is even more significant when you start looking at some statistics. So here I compare the 3 different regions. Sigma Orionis here in the center. And if you see how common is the single component with respect to the narrow and broad component, you can really see that Sigma Orionis seems to be in an intermediate stage here. So you have mostly more or less 50-50 from the single component and the narrow broad component as compared with younger regions where you have more narrow and broad components, and also compared with older regions where you have mainly single components. So it's very cool that you can start looking at these evolutionary trends with age by looking at this oxygen 1 line. But of course, if we think that external photoevaporation is important in this system, now we should also try to see a trend with the projected separation from the massive star. So that's what we did here. So on the right here, you can see the kinematic components of the oxygen 1 line, so the full width at maximum on the top and the peak velocity on the bottom as a function of the projected separation from the massive star. And something very interesting, what we found is that in the inner parts, so where the protoplanetary disk seems to be more affected by this external photoevaporation, we only see single component lines for the oxygen 1 line. So just as we saw for the evolution of the dust, so from the cavity of the disk that produces the single component, that is also something that we found in here, where somehow by losing mass also externally from the oxidine, the profile of the oxygen 1 seems to be also getting into a common mode, which is the single component, which is something very, very, very cool that we found there. So you can really see the difference between the inner parts and the outer parts of the cluster by looking at this line. But of course, the ideal case will be to try to really resolve especially these lines. And that is something that we can actually now do. So this is a work leading by the PhD student Marilise Aru in ISO, working with Carlo and with me. And what we have done here is use MUSE to observe Orion proplets. So we have a sample of 12 proplets in Orion. We know that these proplets are just externally photoevaporating disks that have this peculiar cocoon-like shape that is pointing the ionization front, which is this super bright part here, is pointing towards the massive star here in the trapezium. And what we found here is these beautiful images, beautiful collages of these 12 proplets, where you can really see the emission, especially of the different optical lines and also the H-alpha. So it's a beautiful work that we have done, and in this particular paper that has been submitted and is going to be published very soon, so stay tuned for that. We just wanted to present the sample, the morphology of the proplets and different emission lines, and also measure the ionization front in different lines. And what we found is, well, first of all, we proved through this study that we can actually go and estimate these ionization front sizes for the proplets and different emission lines. And what we see here is that if we compare the ionization front radius as a function of projected separation from the massive stars, we found that this actually increases just as expected from photoevaporation models. But we also started looking at the mass loss rate from these proplets, from the ionization front sizes. And what we see is that, again, the mass loss rate is here, and now the projected separation is inverse here. So we found that the proplets, the protoplanetary disks that are closer to the massive stars, also have a more or higher mass loss rate, which is also consistent with external photoevaporation models. So you can see the power of using this type of observation where you can really go and see where these lines are being emitted is very important. One thing that we highlight here is that, for instance, the sulfur 2 line that has been widely related to jets as well is very, very good tracing the tail of the propellant as well. So this type of a study also is going to help us to have a better view and understanding of what we see in the spectrum, in the spectroscopy data. So stay tuned for that work, because it's very interesting. And now to finish with my summary and my conclusions, we see how Ulysses, and specifically Ulysses in synergy with other sources like Penelope, provides a once-in-a-lifetime opportunity to make significant advances in the study of the physics of low-mass YSO. It has been greatly improved our understanding, particularly in these dispersed dissipation mechanisms. As we can see, we can characterize the inner disk, the molecules, the atomic part, the ionized gas, and also the winds and outflows. And also the data releases really are enormous values for our community, since if we use it in synergy with other YSO surveys or multivalent observations, I believe is where the legacy of Ulysses is. We can have a very holistic view of what is going on in the system, and we can really understand this evolution and planet formation. So I'm very confident that we're going to still celebrate the Ulysses end of the beginning for a long time now. Thank you.
Questions for Karina?
Thanks, Karina. That was really beautiful. I am wondering how the single component oxygen 1 lines in your very irradiated sample, have you had a chance to look yet at how those single component lines compare to the lines from the less irradiated population that only have single components?
You mean like the Basanti sample?
Yeah. Do you have a sense of how the full width half maxes and centrals compare to those?
Well, I mean, you can see it more or less here. This is the comparison with Basanti. So these are the single components, the blue triangles here for Basanti, and these are ours. So they seem more or less in agreement, I guess. The only thing that we found, as I show, was that we found more single components as compared to the younger regions. But I mean, the thing is that in Sigma Orionis, I mean, we're comparing with the projected separation because we have the massive star. And that's something that we cannot do in regions like Taurus and Lupus that doesn't have massive stars. But it seems to be more or less common, but I mean, this is preliminary results, so we really need to just start looking in details to see if we found something interesting. Yeah. Thanks.
Thanks. Very nice. I have two quick questions.
Okay.
One is in the plot where you're measuring the mass loss rates of the propylates, how are you actually observationally measuring the mass loss rates?
Yeah, what we did was, if you see here, you have the ionization front radius as a function of protein separation from the H-alpha line. And what we see, and what we did was compare the ionization front, the relationship between the ionization front and the mass loss rate using these models. So this prescription, which are the purple lines here. So we basically use the relationship between the ionization front size and mass loss rate to estimate this. So this mass loss rate, came from the H-alpha ionization front sizes.
Okay, thanks. And the other quick question is in sort of the plots where you show like full width half maximum versus sort of offset velocity, this one, and I think I noticed one of them earlier back, you've got a few examples. There's one I think there was loads more in the other one where you have sort of quite a high redshift and quite a low full width half maximum.
Okay.
So there's one there that has like a redshift of like 15 kilometers per second and a full width half.
In this one or in
Yeah, in this one example, right? There's a sort of cases that have full width half maximum of like 20 kilometers per second and a redshift of 15 to 20 kilometers per second.
Like these ones?
Yeah. So sort of what's going on in those that make them different to the others?
Yeah, well, that's a very good question. I really have to look at this paper and see why this region have this super high, as you mentioned, red shifted there, but I don't really know what is going on there. I have to check and I'll let you know. Yeah, but that's definitely something peculiar.
Do we have anything online or on Slack, Charles? No. Okay, I think we have time for one more question in the room. Anyone?
Okay.
No, it's just it's very interesting. On these pictures that we see the jet, of course, there's a magnetic field for the jet, and we see the thermal wind, and then we see this MHD wind in the inner part. And
okay.
I keep thinking, what is it with the MHD wind, and where's the boundary between the two, and how do you know this? How do you know there's an MHD wind?
No, what we done so far, for instance, in these optical works done by Simon and Basanti and all of them, what they do is that if you measure the width of the line, so then you assume Keplerian rotation, you can estimate more or less where the emission is coming from, so the radii of the emission, and then you compare that with the gravitational radius of the gravitational potential of the star. So if it's larger than the radii where the emission can escape can be greater, then you can have a thermal operation.
Disentangle the different, you can have components.
Yeah.
You have driving of the wind, and I think of wind, I think the supervising force. And wouldn't it be more logical you have different forces contributing perhaps at the same time? So any location might have a contribution more than one force. Why do you need to have this bimodal sort of MHD process? Is there something specific at that boundary?
Yeah, I think Uma wants to say something about that.
Let's try to use the microphones.
There were two different sort of approaches to this. One was looking at disk dispersal, which is looking at a photoevaporative flow, and MHD disk winds were mostly to sort of explain accretion. And like I was pointing out, so putting sort of thermal physics into MHD models is quite difficult, and it's only been recently available. But I thought I made the point yesterday, but clearly I did not. But I think it's very difficult to decouple the two. And in fact, the winds would be heated, which would affect, I mean, you have UV radiation, you would heat the winds. And in fact, I think if you have to drive accretion through the disk, you should have some sort of MHD wind in the outer disk as well, because And it's absolutely impossible, especially if it's an FUV-driven wind, because the base of the wind is at the same place as where the FUV ionization front is. So whatever MHD wind you're launching, you would have to heat it. So they are sort of, what they call now, I think Shuning Bai calls it magnetothermal winds, because you can't, they're not separate processes for sure. It's just that it's difficult to solve that problem theoretically, and so people have been sort of, assuming these single temperature MHD winds and sort of doing no magnetic fields in the photoevaporative winds. But yeah.
All right, I think we can continue this discussion at the coffee break. We're just about out of time for this session. Let's thank the speakers again. And we'll get started at 11.